wrong with this projector? Okay, here we go. Okay, good morning, everyone. Let's get started. So in the last lecture, we introduced the basic idea about linear models and linear classifiers, right? So basically, linear classifiers are determined by a weight vector and bias parameter, right? So if your input feature vector is x, right? Then a linear classifier is determined by a weight vector, same dimensional with x and one bias parameter, right? And then when we do the classification, we just calculate the score, right? The score is actually a linear function of x, w transpose x plus b, right? Then we just look at the sign of this score, right? If it's positive, we predict this positive label. Otherwise, we predict the negative label. That's the definition of linear classifier. And we have explained some kind of geometry intuition about linear classifier. Actually, linear classifier determines a linear boundary, which kind of partition the instances into positive, negative, right? All the examples on one side are positive, on the other side is negative, right? So if it's two-dimensional plane, it's a line. The boundary is a line, right? If three-dimensional, the boundary is a plane, and if it's higher dimensional, it's called hyperplane. That's the basic idea about linear classifiers. Any questions so far? We just have a quick warm up. Okay, so today we're gonna start looking at specific learning algorithm for linear models, right? Because linear classifier is kind of a large topic. We're gonna start with linear regression, which we call least mean square regression, because linear regression, the typical learning approach is just gradient descent or stochastic gradient descent. So we're going to start with linear regression, and then we'll proceed to several classical linear classifier learning algorithm. Okay, so here's our plan. Sorry. So we're going to first introduce some concrete example to illustrate the model of linear regression, and then we're going to discuss what is appropriate training objective to train a linear regression model, right? So we call it least mean square objective. And you see that it actually comes out from the definition of the so-called cost function. Then we're going to talk about how do we optimize this objective function to find out the model parameters, right? So actually you will see that in most machine learning applications, the training essentially is to optimize some kind of objective function defined on the training data, right? So you want to, in some sense, find out a set of model parameters which can make your model to fit the data, fit the training data as good as possible. Of course, there could be some trade-off, right? But this kind of trade-off, all data fitting, is all reflected in the so-called learning objective function, right? And then we want to kind of optimize this objective function to find out the model parameters, right? So this mean square regression is the first typical example we're going to discuss. Okay, so let's start with a application, right? It's very simple application. Suppose we want to predict the mileage of a car from its weight and age. So here, we're going to represent a car with two features. Right? One is the weight of the car. The other is age of this car. And then we want to use these two features to predict the mileage you have driven this car, whatever. The car owner has driven this car, right? And so this is a typical regression problem, right? So here, this small table give you some kind of like sense, the data. Right? So we have a X1, age, and the mileage. And of course, this mileage is like, should be 21K, something like that, right? And weight, second row corresponds to another car. 36.2 age, 2 years, and 25K mileage, and so on. Right? So from this piece of training data, what we want is a function that can predict the mileage using the new features, the new feature values of x1, x2. Okay. Is that clear to everybody about this problem formation? Okay. So, and now we're going to think about how to we use linear regression to solve this problem. Right? So what is linear regression? Linear regression assumes the output here, it corresponds to mileage we want to predict, right? Is just a linear combination of the features. So we have two features, weight and age, x1, x2, right? So we're going to linearly combine them plus some bias term W0. So we get our prediction of the mileage. This is our model, right? We model the mileage as W0 plus W1, x1 plus W2, x2. Okay? So this is our modeling and also our assumption. The learning amounts to using the training data to find the best possible value of W. And here, W corresponds to these three weights, right? W0, W1, W2. Okay. And once we have identified W through training, given the values for x1, x2 for a new car, we want to use the learned vector W to predict mileage for the new car. So this is a whole framework. Does it make sense? Okay. So now we can extend it to a more general scenario, right? So in general, let us assume our feature input feature vector from a d-dimensional space. And here for simplicity, let us assume the first feature x1 is always 1. So this is like a simplified notation technique, right? We add a constant feature 1 into our feature vector. Right? So any feature vector can be represented as 1, x2, x3 to xd. Okay? And then we have collected a training set, m pairs of input feature vector and output value y1. Right? Then in the linear regression model, we're gonna approximate output y as a linear combination of those features. So remember, x1 is 1, right? So our linear regressor has this form, w1 plus w2 x2 plus plus wd xd, which can be further simplified as a dot product between the weight vector w and the feature vector x. Right? Does it make sense? Any question? So this is a general framework. Right? Is everyone comfortable? Okay. So now we're going to instantiate this linear regression with several concrete examples, right? First, suppose we want to do one-dimensional regression, right? That means your input feature is just a number, right? And then you can imagine our training data points like this, right? So you have different features x, right? So remember here we put x2 because x1 is fixed as constant feature 1, right? We can view it of doing this is to accommodate this bias term, right? W0, right? And then we want to learn a linear regressor model. In our case, now it will be a line, right? And we want to, the learning essentially is to move this line, placing the right position and angle such that it can be the closest to all the training data points. And we can consider two-dimensional space, right? So suppose your feature vectors are two-dimensional. That means your x-axis, your x-axis, your feature, your input vector are just the points, right? Just points on this x1, x2 plane, x1, x2 plane. Then you have some y values, which are represented as red dots here. Okay. Then our linear regressor essentially is trying to is expressing a plane, right? And it tries to, like, you can imagine you try to move this plane and to be as close to those red dot, the training points, as possible. That's the idea, right? And of course, you can extend it to a higher dimensional space. Imagine in a higher dimensional space, you have a bunch of data points, which are your training set, right? And then your linear regressor actually determines a hyperplane and want to move this hyperplane to be close to those training points. And how do you move that? That's the thing we're going to discuss in next step, which we call training. Okay. So let us talk about, right, what's the best weight vector, right? So we know that those weight vector determines the position of your plane, your hyperplane, right? The position where your linear regressor is, right? There comes a problem, right? How do we know which weight vector is the best for some training set? Okay. Any thought? What kind of criteria should we use to check if some weight vector is good or not? Some weight vector is best as compared with other possible weight vectors. Any thought? Compute what? Okay. Yeah, that's a good idea. Yeah, that's definitely a good idea. You have some? Okay. Any other thought? Yeah. Okay. So one possible measurement is that, okay, I'm gonna come out some kind of measurement which can quantify how close your hyperplane is to every data points in your training set, right? So, so now let us follow this idea and propose some kind of measurement, right? So imagine you have already had a linear classifier. No, sorry, it's not linear regressor, right? And this is weight vector, right? Given any input vector xi and output yi, right? So I can use my linear regression model to make a prediction, right? Which is W transpose xi. Everyone agrees with this, right? And then I can look at how much my prediction is deviating from the ground truth yi, right? Now, obviously, the larger from the ground truth, the worse. So can make an analogy like, okay, this difference between the ground truth output and my prediction as kind of like cost of making a mistake. Okay. You make a mistake, and then you have to pay some cost, right? And the larger difference your prediction is from the ground truth, the more cost you should pay. So you can use this difference, absolute value of the difference between your prediction and the ground truth as a measurement of cost. And then I can look at, for every training example, what is my current model in terms of cost, right? And then I want to have their total cost as a measurement. And here, for simplicity, right, for the convenience, right, we take the square of the cost in predicting each training example, then add them together. We use this guy as a measurement to quantify whether your linear regressor is good or not. It's just for convenience to calculate the gradient. If you want to calculate gradient, you see you have some power 2 here, right? and you take the gradient, the power 2 will move to the front and cancel out, and that's it. But you can definitely throw it out if you don't like it. There's nothing other meanings than this. Any other question? Okay, so I want to emphasize again because this is really important, right? So given our model definition, we know in the model space, right, there could be like infinitely many possible linear regressors. Each one represents a particular line or particular plane or particularly hyperplane, right? So we want to decide which plane is the best regressor, right? So that drives us to come out some kind of quantitative metric, right? So a natural quantitative metric is the so-called cost function, right? Basically, we want to look at for every training input, right? What's the difference between my prediction and the ground truth? And the larger the difference, and you should pay more cost. And overall, want to look at, okay, what is the summation of all the cost on the training set, right? Which we call total cost on the training set. And they want to minimize this total cost. And for convenience, like a very commonly used cost function is called square loss function, which is just to take the square of the cost and sum over all the training examples. And then we use this number to quantify how well your linear regression model fits the data. And then if we want to find out the best linear regressor, how should we do that? Any thought? We have already come out some metric to judge how good your linear regressor, right? And then how can we find out the best linear regressor? Yeah, so we can just minimize this total cost function, right? We just minimize this and find out, okay, among all possible planes or hyperplanes, your instance space, which one can make this total loss or total cost to be the minimum, right? And then we'll that kind of like that particular hyperplane the best linear regressor. That's the idea of the training of that is the idea of the least mean square training. Does it make sense? Right? Okay. So our strategy of learning is to find out the weight vector with the least cost on this whole data set. That's called least mean square regression, right? And of course, you can seek for other strategies for training. And here we just introduce one strategy, that is to minimize the least mean square cost function over the training data. You can definitely define other cost functions, right? So here we use the square of the cost, right? Square the absolute difference between the prediction and the ground truth as our cost. And in some other places, some other works, they're gonna take some power of Q, and Q is less than 2. There are some like benefit of doing this. And in a extreme case, you could take Q equals to 1. That means I just minimize the summation of absolute difference between your prediction and the ground truth. Right? That's another cost, right? So it basically depends on how you're going to define your cost function, right? And then you can optimize your own version of the cost function to find out the model which you believe is best. But the most popular one, or perhaps also the simplest one, is just take this squared difference as the cost and minimize their summation. The reason is simple, because when you calculate the gradient, it has a very nice closed form. It's very easy for calculation. Okay, any questions so far? Well, because the original literature this is not half, is 1 over m. There's no difference. Because when you minimize this guy, it doesn't matter if you multiply the sum with 1 over m or with 1 over 2. Good question. Any other questions? Okay. So now let us proceed to this training procedure. So our training, or also known as learning, is to minimize this sum square error with respect to model parameter w. So now we have convert because the training now is converted into an optimization problem, right? So the remaining question is that how do we do this optimization, right? Here we're going to talk about gradient descent based approach. Right? This is that because this is the most popular approach. But we would like to mention later, for this particular minimization objective, there is also an analytical solution. Actually, you can derive it by yourself. Okay, so what is gradient descent, right? As the name suggested, right? It's a way to optimize model parameters of interest following the gradient's direction, but it's kind of opposite to the gradient direction, right? So if we take a look at this example, right? So here's the general strategy, right? Suppose you have some objective function j, right? And we're gonna start with some initial guess for w, right? And say w0, right? So in many cases, you probably just initialize w vector as 0, or you initialize them as random numbers, sample from Gaussian distribution or uniform distribution. Then you perform the following iterations until convergence. So inside each iteration, we're going to compute the gradient of our objective function j at current weight vector, denoted as wt. And then we update wt to get that wt plus 1 by taking a step in the opposite direction of the gradient. So that's why it's called gradient descent, right? So if the gradient is this way, you're going to update your model parameters in the opposite direction. Right? If the gradient is this way, you're going to update in this way, right? So this figure shows like why we should do gradient descent when we minimize some objective function, right? So this is a quadratic objective function, right? It's a quadratic function. Right? So suppose you start with some initial position w0, right? If you calculate the gradient, it will be the slope of the tangent line, right? And this tangent line has positive slope, right? So what's the slope? What is the slope? What's the definition of slope? What? X equals to y? X over y. Yeah. But more formally, the slope of any line, right, is just if you take the angle from the line and the x-axis, right? The slope is tangent of this angle theta, right? This is definition of slope, right? So that basically means like, okay, if this angle is less than 90 degrees, the slope is always positive, right? Otherwise, the slope, if you have a slope, have a line along this direction, right? The slope is negative. So the gradient actually is the slope of the tangent line to this function body at w0, right? And we see the slope is positive. That means your gradient direction is toward the right, right? And now we perform the gradient descent, meaning that we're going to update our W to the left. So that's how we get W1, right? You see, it's kind of like a moving toward the minimum of the function, right? Why? Because if you move toward the gradient, you're actually increasing the function, right? And if you want to minimize function, you need to move toward the opposite direction of the gradient. Right? That's why it's called gradient descent. So keep doing this. We got W2, right? You see the slope is also is still positive, and so you're gonna move the you're gonna update your weight to the left, right? So you get W3. And just keep doing this, Eventually, you're gonna converge to this minimum. So that's the idea of the gradient descent. So the gradient is the direction of the increase in the function, right? To go to the minimum, go in the opposite direction. Any question? Okay. So now we just apply this updating rule and to perform to fulfill our least mean square regression, right? So here is the algorithm framework. Given our objective function, which is the summation of the squared cost square loss, right? And divided by 2 is just for convenience, right? We initialize our weight vector W0, and you can initialize it with arbitrary values, right? Then it goes through iterations. For each iteration, we're going to compute the gradient of the objective function at current W, right? Which is denoted in this way, right? And then we just use this rule to update our weight vector. So you see WT plus 1 is calculated from subtracting WT by the gradient with respect to WT times a small positive number R. Right? This R is called learning rate. It actually determines how much you would move along the opposite direction of the gradient, right? And intuitively, you don't want to move too much, right? If you move too much, it's not guaranteed to decrease, right? But you don't want to move it too slow, right? So you want too small so that your optimization becomes too slow, right? So the choice of the learning rate actually is pretty important in practice. But for now, let us assume this R is just a small constant, and we'll get to this later. Okay, so the remaining part for this algorithm framework is to figure out how to compute the gradient of the loss function or cost function with respect to the weight vector W, right? So once we have this gradient, we can just apply this formula to update our model. Right? So now let us look at the gradient of cost, right? So first, this also goes back to our homework 0, right? And we asked you to write down to calculate some gradient manually, right? It's just to prepare for this. So here we look at W, right? W is actually a vector. So imagine you have like 12 features, and then your W will be a vector, 12-dimensional vector, right? So that means the gradient of the cost function is also a vector. Each element in this vector is a partial derivative of the cost with respect to the corresponding weight, right? So remember, W is a vector with D elements, right? So now let us try to derive the formula of the partial derivative of the objective J with respect to one particular weight Wj. That is the jth element in the weight vector. Right? So we're going to take the partial derivative of this summation of the square loss with respect to WG, right? And of course, we can move the partial derivative operation inside the summation and take a look at each squared cost, right? So here it just practice calculus 1, right? So you take the derivative of the square term, you're gonna move 2 in front of the expression, and then times this difference, right? yi subtracted by your prediction, and then apply the chain rule. You're gonna take the partial derivative of the error or difference, right, with respect to WG. And if we look at this dot product, we'll see that this is essentially W1 times the first feature of xi, right? Which we denote by xi1, right? W2, the second feature for xi2, right? And so on. Because we are only interested in the partial derivative for WG, right? So there's only one term which is relevant. Okay? That is WG times the jth feature of xi, which is xij. Okay? So this is a linear term. If you take the derivative with respect to WG, it will becomes xij, right? So now we have got our derivation, right? So for each I, right, the partial derivative of this yi subtracted by w transpose xi will be minus xij. Right? Now you just sum over the partial derivatives for every example I. You got the total partial derivative with respect to WG. Does it make sense? So this is just like a typical application of the derivatives and chain rules. Okay, we can move the minus sign in front of it and cancel this 2, right? Half and 2, you get our final form. And through this form, we can calculate one element of the gradient vector. And this is not done yet, right? We need to calculate every element of the gradient vector to find out our gradient vector. Any questions so far? Okay, so again, we suggest everyone to manually replicate this calculation after the class, right? That will deepen your understanding about how this gradient computation is done, right? But now if we look at the structure of the gradient, we find this very interesting. Right? So it's a sum, right? It's sum over all the training examples. Inside the summation, right, each summand actually is the error. The error is the difference between the ground truth output and your prediction, right? Times the jth feature for every input vector, right? So you can see that because right now we're computing the partial derivative of the loss function with respect to the jth weight, right? And the result turns out to be, okay, this is summation of the prediction error times the jth feature in data, and then take minus them. That's it. Okay, so now we can apply our calculation to get the gradient, the element, every element of the gradient, right? And then once we have collected all the gradient elements, we're gonna update our W using this gradient descent. And just keep doing this, right? Every time, every iteration, we're gonna calculate the gradient of the objective function with respect to the current weight vector, then calculate the gradient, and then update the weight vector. Just keep doing this until it converges or some total error below some threshold. This is a typical gradient descent learning framework, not only applied to least mean square error. Actually, we can apply to whatever objective function. For example, you can replace this guy by a loss function for neural networks, and you are doing this. Right? This is actually pretty standard in the deep learning training stuff nowadays. And again, we want to emphasize the small constant R here is called learning rate, right? So modern machine learning algorithms has a lot of tricks about how to choose R and how to schedule R along with the training iterations. Okay, going back to our least mean square problem. We want to emphasize this algorithm is guaranteed to converge to the minimum of J if the learning rate R you chosen is small enough. Why is that the case? So this is actually some theory from optimization. Actually, for any objective function, differentiable objective function, if you use gradient descent, if you choose every step you choose R to be appropriately, it will guarantee you're going to converge to some minimum of the objective function. Right? But here we have even stronger results. The objective function is the convex function. So remember what is convex function, right? We'll discuss about that, right? So if you have a convex function, then this gradient descent will guarantee to converge to the local minimum. So that's the advantage of convex function. Okay. Any question before we discuss the next version of the gradient descent? Everyone's comfortable? Okay, that's great. Because you're gonna leverage this framework to implement your least mean square regression in homework too. So just make sure like you're comfortable with this, right? Okay, so now gradient descent is definitely straightforward and also seems convenient, right? But if we look at the structure of the gradient, right, we see that to calculate every gradient element, you have to perform the summation over the entire data set, right? You're gonna sum over example 1, 2, 3 until m, right? So this might not be some issue when your data set is small. But what if your data set is super big? Suppose you have like 1 billion training examples, which are not uncommon in nowadays applications. So that means even to perform one single gradient descent, you have to go over the entire data. You have to pass through the entire data set, right? That means you have to pass through the whole 1 billion training examples. Then this will be very, very expensive. So in this, in big data scenario, this gradient descent sounds like very slow and very ponderous because the weight vector is not updated until all errors are calculated on the entire training set. So that motivates people like to think about, okay, is there any efficient way of performing update of the model parameters? Any thought? Do you have any heuristics or guess or intuition about how shall we update the weight vector W to be more efficient? Mm-hmm. Yes, yes, perfect, right? So this is very intuitive, right? So now that the standard gradient descent requires you pass through the entire data set, like 1 million or 1 billion data points to get one gradient and to update, right? Why not we just partition the data, right, into many, many small batches, so just 100 examples, right? As long as I have calculated these errors, right, for 100 examples in this batch, and then I just add them together and then update my model parameters. Right? So no matter whether this is correct or not, at least it's kind of like much more efficient than just performing the standard gradient descent, right? Imagine like you have 1 billion training examples, right? And you get one single update with the gradient descent after you pass through the whole 1 billion training examples, right? But if you use like updating per 100 examples, once you have passed through the whole data set, you have a updated model for, I don't know, 1 billion over 100. is I don't know, 10 million updates, right? And you have updated the model, you have evolved models a lot, right? A huge amount of times than just performing the standard gradient descent. Okay, so this type of idea is called stochastic gradient descent. So this is not only showing to be very, very useful in practice, it also have very, very strong theoretical guarantees. So basically, if you're doing this, right, you just collect a batch of training examples and calculate the error and multiply the feature and add them together as a substitute for the gradient to perform the update. Of course, this kind of approximation is not accurate, but if you perform a lot of times, like on average, you're gonna still close to the true gradient. But the benefit is that, okay, I'm gonna update my model much more frequently, tons of more frequently than just performing standard gradient descent. Right? So this is called stochastic gradient descent. Right? So the stochastic gradient descent, the idea can be summarized as follows. So we can repeat for every training example xi, y. We pretend the entire training set is represented by this single example. Then we use this example to calculate the gradient, the updated model. Okay. So you can imagine if we're doing this, the gradient you computed is no longer the exact gradient over the entire data set, right? It will be a very, very rough approximation to the exact gradient, right? But the benefit is you can make millions of updates when you pass over the entire data set, right? And then the question is that millions, is this a approximation worth, right, our quick updates? The answer is yes. Actually, in many cases, you see that using stochastic gradient descent is way better than using gradient descent. Not only because it updates your model more frequently, but also it can converge more quickly. We'll get to some kind of theoretical conclusion later. Okay, so here is our stochastic gradient descent framework. So we initialize our wave vector W. Then we go through this big T epochs, T from 1, 0, 1, 2, 3, and so on, right? And then we're gonna sequentially pass through every training example, X, I, Y. Then we treat this particular example X, Y, as the entire data set, then calculate the gradient. Then in this gradient, you see that, okay, there is only one component, right? That is the error difference between the yi and your prediction times the j's feature, right? And then you do the gradient descent, you subtract it by this gradient descent. There will be two minus sign here, and they will go positive. Right? So this is different from the batch gradient descent or standard gradient descent in that the batch gradient descent will require us to go over all the training examples in this data set. Then we finish calculation of the gradient vector and do the update, right? But for stochastic gradient descent, whenever we have processed one example, we're going to update our model. So suppose you have 100 examples and going through this procedure, you're going to update the model for 100 times. Okay? When you pass the data set for once, right? But for gradient descent, right, you only update the model once. Right? So this updating rule is also called Virchow-Hopf rule in the neural network literature, but was originally invented by those neural network people from their intuition. Right? Later, and people have proven all kinds of amazing theoretical guarantees for this type of approaches. Right? So when shall we apply stochastic gradient descent? As we mentioned, right? It is preferred when your training set is very, very large, and it is not very efficient to load all the data set into your memory and go through the data set one time to just calculate one gradient. So in this case, stochastic gradient descent dominates. And it is often case that applying stochastic gradient descent can get close to optimum much faster than the batch version. That's why nowadays all neural networks are trained by stochastic gradient descent. Examples? Yeah. Yeah. So basically, we'll apply the stochastic gradient descent, right? You're gonna go through this training set one by one. But every time you look at one training example, you perform one update, right? So imagine that you have finish one path of this training set, you have a perform like as many as the number of the training examples in set for the model update, right? But if you're doing the standard gradient descent, okay, just update once, right? So, and of course, in practice, when a data set is super large, it is possible that even the model could even converge before you have seen all the examples. So, that's a very amazing property of the stochastic gradient descent. But in practice, people will usually, okay, I'm gonna run, or I'm gonna still go through this data set multiple times, right? And one pass to this data set is called one epoch, right? And you're gonna go through this data set for 100 times, 100 epochs or 1,000 epochs. It's often is the choice is flexible. Yeah, yeah, we always want to use the whole data set because we want to leverage as much information as possible, right? The question is that how do we more efficiently utilize the data information to update our model, right? We don't want to go through 1 million examples until we finish one update, right? We want to when we see some data points, I'm gonna update myself. When we see the next data point, I'm gonna update myself, so I can update my I can update and improve my model very, very quickly. Yeah, yeah. Yeah, that's why it's also called online algorithm. So like, okay, you have this current model, right? You have you're deployed online, and then every once in a while, you're gonna collection of new data points. You want to pass through this new data set to get a model update. So this framework is also frequently applied in this online or streaming version. Any other question? Okay. So now we should talk about R, right? So we see that in both standard gradient descent and also stochastic gradient descent, you have to choose a learning rate R, which controls how much you want to update the model according to current gradient, either the gradient or either the stochastic gradient, right? So in general case, if you want to show convergence, you must make sure your learning rate R decrease to 0, right? And if you got a chance to look at the proof, actually, they're gonna use this sequence of decaying sequence of R to control to construct some sequence to guarantee the convergence. That's why theoretically you should make your learning rate R. You should schedule learning rate R to be decayed to decaying and converge to 0 in a limit. Right? And then this learning rate in some other scenarios is also called step size. Right? So there are a bunch of sophisticated algorithms to help you choose the step size automatically and make your convergence faster. For example, nowadays, like the most popular stochastic gradient descent learning algorithm is called ADAM. Right? It is a way to dynamically update or dynamically schedule the learn rate R for every step and then for every model parameter. So the model parameter can vary. Okay, this is about learning rate, right? Later we'll talk about the several classical schedules of the learning rate, which guarantee the decaying to 0 and also satisfy other requirement for the convergence of stochastic gradient descent. And in many cases, choosing a better starting point can also have an impact, especially when your training loss is not convex. If it is convex, and if you could wisely choose the starting point, it will converge faster. But if you choose it to be far away from the minimum, it could be converged slower, right? But anyway, they're gonna converge to the same place. But for non-convex objective function, like very vivid landscape, right? The performance of your learning is highly dependent on at which places you want to start, right? So if you want to start here, then it could converge here, right? If you want to start it here, then it could converge here, right? As obviously the latter has even smaller objective functions values, right? Okay. Overall, the gradient descent and its stochastic version, in general, is a very simple algorithm, right? But almost all the algorithms we will learn in the class can be traced back to some kind of gradient descent, including the perception algorithm we're going to discuss in for the next topic, right? And machine learning essentially is just to repeatedly apply gradient descent or stochastic gradient descent for different loss functions and different hypothesis spaces. Okay, so now we have finished our discussion about linear regression. In summary, the objective or the goal for linear regression is to predict a real valued output using a feature representation of the input, right? And the key assumption of linear regression is that we're going to assume the output is a linear function of the input, is a linear combination of the input variables, right? And the learning is really conducted by minimizing a total cost over the training data, right? And once we have decided the cost function, we can use gradient descent or stochastic gradient descent to optimize this cost function and find the best weight vector. Any questions so far? Okay. Okay, so the last thing we want to point out is least mean square regression can be solved analytically. Suppose you have a data set, right? And you have output y, right? You can represent your input feature matrix, your input feature is this matrix, right? Your output value is a vector. Then your objective function can be written in this way. And then if you take the gradient of your objective function with respect to the vector w and solve this gradient to be 0, you will get the closed form solution for this, right? And again, I will leave it as an exercise for you. Okay. So next. We're going to discuss perception algorithm. Okay. So now we'll proceed to the linear classifiers. Right? So I'll wrap up the discussion about linear regression, which is relatively easy, just doing some optimization over least mean square objective function, right? So now we talk about, now we switch to linear classifiers, right? So the very first algorithm we want to talk about is called perception algorithm. So as later, we'll see that shortly. The perception algorithm is a very simple and online algorithm. And it's also called lazy algorithm, meaning that it only updates model when the model made some mistakes in predicting some kind of examples. Otherwise, it won't change the model. However, this simple algorithm has some kind of elegant theoretical properties, which we call perceptron mystic bound. And later, we'll talk about the practical variance of perceptron. How do you make a modification of perceptron to make it more practically useful? So first, perceptron algorithm. Right? So we need to first recall the definition of linear classifiers. So basically, linear classifiers deal with, in general, n-dimensional feature vector, and the output is a binary label, -1 or 1. And linear classifier, also called linear threshold units, classify examples using this rule, right? So we will have a weight vector W and bias parameter B, and we'll calculate our score by the dot product between W and X plus B, right? Then we look at the sign. If it is positive, then the prediction is 1. Otherwise, the prediction is -1. And graphically, it can be this classification procedure can be represented as some kind of like basic block, right? So you have your input features x1, x2, and to x8, and some constant feature 1, and then through w1, w2 to w8, and also bias parameter b, you can multiply those features and aggregate them in an intermediate node. This intermediate node just doing the summation, right? And then you have this score. Right? You put this through this score into a second unit, which is just taking the sum. Then that will give you the label, either positive or negative. Right? So this is one way to graphically represent linear classifiers, and as we'll see later, this is often used to represent the basic unit of neural networks. Right? And later, I mean, near the end of semester, when we introduce the neural networks, we'll look at this again. You see that linear classifier essentially is just one particular basic unit of neural networks. And some geometry properties of linear classifier, right? And the classification boundary actually is determined by this equality. That is, the score equals to 0, right? And it represents I represent the kind of linear boundary, right? And partition the whole instance space into 2 half spaces. One half space contains all the positive examples. The other half contains all the negative examples. Okay, so here comes a question. Given our definition of linear classifiers and given all those positive and negative examples, how do we determine at which position we should place the linear the classification boundaries? Right? So there can be a variety of learning algorithm, right? The very first one is called perceptron, and was proposed by Rosenblatt, and this is a pioneer of the machine learning and artificial intelligence. Although at his time, like there's no word called machine learning. But when the perceptron algorithm was first proposed, it was so hot and inevitably brought some hypes. Right? This is some kind of snapshot of the New Yorker's paper, right? They show that okay, the scientists are implementing perceptron algorithm on this IBM 704 computer. It's kind of like a superpower computer at that time, but right now the power might be less than a portable calculator, far worse than your iPhone, right? And but at that time, people are very optimistic and believe that perceptron will soon shown to be intelligent, right? Can do all intelligent things people can do, right? But it turns out this is kind of like a over optimistic, and it's far away. Right? It's far away from being truly intelligent. Okay, some kind of like a history of perceptron algorithm. It was first proposed by Rosenblatt in 1958, right? And the goal is just to find a separating hyperplane, giving you 2 sets of data points, right? one is positive, one is negative. Can you find out a hyperplane to well separate positive and negative examples? Right? So the algorithm itself is an online algorithm, meaning that it's going to sequentially go through every example in the training set and make update if necessary. And later there are a variety of variants. Okay, so here is the original perceptron algorithm. So let us look at the algorithm table. Right? So our input is a sequence of training examples, pairs of x1, y1, x2, y2, and so on. Right? And each xi is an n-dimensional feature vector. The label yi is either -1 or 1. Right? So the perceptron runs as follows. So first, we're going to initialize our weight vector to be 0, meaning just a 0 vector. Every element in the weight vector is 0. Then we're going to go through every training example xi, yi. We use the current model WT to make prediction on xi, right? And our prediction is denoted as y prime, right? If y prime is not correct, meaning that it's different from the ground truth label, yi, then we update the weight vector with this rule. Right? So this WT plus 1 is obtained by adding WT with this R times yi xi. So R here is also called the learning rate, right? And then you look at the next example, right? And then use your model to make a prediction for the next example. If the prediction is correct, you do nothing. Otherwise, that means your prediction is wrong, right? You're gonna apply this rule again to get a new version of the weight vector, right? You just keep doing this until you have exhausted all the training examples, right? And you return the final weight vector. Any questions so far in terms of the yi? Even this one? No, because right now we didn't try to give any loss function on this, right? We just give you updating rule. It's a heuristic rule. Yeah, we're going to discuss about it. Yeah, we're going to discuss why it works and why from intuitive way, and later we'll justify this is indeed a kind of gradient descent, but it's not gradient, it's called sub-gradient descent, right? But looks like this form is kind of similar to gradient descent, right? But right now we're not talking about any loss function for perceptron algorithm, right? So right now let us treat it as just the heuristic rule. Actually, when Rosenblatt proposed his perceptron algorithm, he just proposed this updating rule from intuition. No like rigorous justification on this. So here, we want to emphasize that this xi is of like augmented feature with some 1, so that our weight vector W has some Bass parameter inside it. This kind of notation convenience, right? We have illustrate before, right? So we don't want to directly write out the weight vector and Bass parameter. So I want to inject the constant 1 into the feature vector. So then my dot product between W and X actually is implicitly doing like the dot product between the original weight vector and the feature vector plus the Bass parameter, right? And this is the notation trick we have discussed previously. Okay. And here we additional note we want to mention is that okay, your label is either -1 or 1, right? This is just for convenience, right? You can also choose another commonly used notations like okay, it's either 0 or 1, right? And then you just need to change this algorithm a little bit. So how do you change it? Any thought? If we specify that yi is either 0 or 1, right? How do you modify this perceptron algorithm correspondingly? Of course, you cannot directly apply this rule, right? If y is 0, that means you don't update the model at all, right? Then what should we do? Yeah, something like this, right? So we know that when yi is either -1 or 1, then this guy is that means you're multiplying this xi with either -1 or 1, right? But now yi, if it's switched to the range of 0 and 1, you can simply map it back to -1 and 1, right? So one common use approach is just replace y by 2y minus 1, right? So you see that when y is 0, it is -1. When y is 1, it's 1, right? So then you kind of like recover the original perception algorithm. Okay. So now let us figure out why doing this is good, right? So what's the rationale of performing an update like this, right? To explain why this updating rule is reasonable, right? So let us consider two cases, right? First, if your example is a positive example, meaning that your yi is 1, then your update is actually here, right? Because y is 1, right? So you're actually adding wt to r times xi, and you get wt plus 1. And if you're making a mistake on an active example, meaning that yi is -1, right? So your update will be subtracting wt by rxi, right? According to this rule. Right? So now let's see why doing this can help us and improve our model, right? So here r is a learning rate again, right? And here is also a small positive number less than or equal to 1, right? And second thing from this algorithm framework, want to emphasize the model is only updated on error. So only when your prediction doesn't match the ground truth label, you're going to update the model, right? Otherwise, you don't update the model at all. So this is a mistake-driven algorithm or lazy algorithm. So of course, this is the simplest version, and we'll see more robust versions at the end of our discussion. And last thing I want to mention is that, okay, when we check whether we make a mistake, right? We don't necessarily need like to look at, okay, your prediction and look at the sign and then look at if your sign is the same as the ground truth, right? You can just check this way. You can just check whether the production of yi, wi transpose xi is negative. Why? Why can we use this to determine if we make a mistake or not? Yes, exactly, right? So this is a very useful trick. Whenever you make a mistake, actually your score will have a different sign from the ground truth label, right? If it is positive, the ground truth is positive, then the score must be negative to make a mistake, right? So their product must be negative. If your ground truth is positive, then you must make a negative prediction, right? That means your score is negative. The product is also negative. So in whichever case, you can always use this inequality to check whether you make a prediction or you make a wrong prediction. Okay. So here is the intuition behind our updating rule, right? So let us start with positive examples, right? Suppose you have a positive example, that is y is 1, right? But you make a mistake, that means, okay, your prediction score, W transpose X, is less than 0, right? Now, we're going to have a new weight vector following the rule, which is here, right? You're going to add X to the current W, right? Because R is 1, right? And let's see, after we have got this new weight vector, do we have a better chance to correct the mistake? To see this, we just want to say, okay, with the new weight vector, what's our score? Which is WT plus 1 transpose with X, right? From the updating, right, we know WT plus 1 essentially is to add WT to X, right? Now you use this new weight vector, dot product with X, and you will see that the new score is actually O score plus X transpose X. X transpose X is the square norm of X, which is positive, right? Okay. So that means after our perceptron update, the score of the model is bigger than the score of the previous model. Is it a good sign? The reason is yes. Why? Because the previous model has made a mistake, right? The reason of mistake is that your score is too small, right? It's below 0. That's why you make a mistake. Now, through my updating rule, I can increase my score. It actually update the model toward the right direction, right? If you want to correct a mistake, you want to correctly classify this positive example, you must make your prediction score to be positive. So that means at least you need to increase your score. That kind of explains why this perception update is reasonable, right? Because it is a update the model toward the right direction. In that, I'm gonna increase the score and trying to be positive so that I can correctly classify this example, this positive example. Does it make sense? Yeah. No one knows. There could be the case that you kind of like correct the mistake made by the previous version, but you made an additional mistake on another example, which was correctly classified. It is possible, right? But this is their logic, right? And later we'll show some theoretical guarantees. As long as your data set is separable, then you always run your perception algorithm. You always find you a separating hyperplane. Right? If your data set is not linearly separable, meaning you cannot use any linear boundary to separate them out, then the perception algorithm will not stop. We just keep correcting this mistake and creating new mistake and creating this thing and creating some new mistakes and keep cycling with this. We're going to discuss about this later. Mm-hmm. No, we don't know that. That's why. Yeah, word here, I'm very careful about the words I'm using. I'm updating the model toward the right direction. I'm not saying my model will cure this mistake, will address this mistake. But at least it's kind of push the model toward the right direction, right? But I'm not guaranteed that, okay, after you kind of increase the score, it's gonna pass 0, right? Bigger than 0 and the correct mistake. There's no guarantee of that as well. Go to the next one. Yeah, go to the next one, go to the next one, go to the next one, and do the cycle. Okay, very great question. Any other question? Okay, I think we can let's stop here today because to illustrate clear about the intuition, we need some like more time on this. Okay, see you on next Tuesday.